Right now, as you watch this, a machine is dying. It has been dying for years, slowly, patiently, the way ancient things die, not in an explosion, not in silence, but in a long, graceful diminishment that we have been tracking, measuring, and dreading since 1977. It is, at this moment, 23.5 billion kilometers from Earth. 23.5 billion kilometers. The signal it sends home travels at the speed of light, the fastest thing in the known universe. And it still takes 22 hours and 35 minutes to reach us. 22 hours. For a signal moving at 299,792 kilometers per second. That signal, that pulse, is not a broadcast. It is not a beacon designed to be heard. It is a whisper, a technical whisper. A stream of engineering data and scientific measurements sent by a machine that does not know it is dying, does not know it is alone, does not know that the people listening to it on the other end have been doing so for nearly 5 decades and are beginning, quietly, to prepare themselves for the moment when it stops. And one day, maybe sooner than anyone wants to admit out loud, it will stop. What happens then is something no human has ever had to reckon with before. Not because it is catastrophic, not because it will change life on Earth in any immediate practical way, but because Voyager 1 is not just a spacecraft. It is the furthest thing we have ever sent into the universe, and when its signal ends, we will be left alone in a way that we have not been alone since before we knew the stars had names. This is that story.
It begins with an alarm clock. On the morning of September 5th, 1977, NASA's launch director at Cape Canaveral set a countdown for 8:56 a.m. Eastern Time. He was not launching a crewed mission. He was not launching a telescope. He was launching a machine roughly the size of a small car, 722 kilograms, that he, and almost no one alive at the time, expected to still be operating in the year 2024. The spacecraft's name was Voyager 1. Its mission, in the original 1972 planning document submitted by Gary Flandreau of NASA's Jet Propulsion Laboratory, was to last 5 years. 5 years. To visit Jupiter and Saturn, photograph their moons, and return data that would keep planetary scientists occupied for a decade. That was the ambition. That was the contract. 5 years, 2 planets, and then silence. The spacecraft carried 11 scientific instruments, a camera system, a magnetometer, a plasma science instrument, cosmic ray detectors, and, fastened to its side like an afterthought, though it was anything but, a 12-watt radio transmitter, 12 watts, the power of a refrigerator light bulb. This is the device that has been broadcasting Voyager's position, health, and scientific data across the solar system and beyond for nearly 5 decades. 12 watts of signal, crossing a void so enormous that by the time it reaches Earth, its power has diminished to a number that requires scientific notation to write 0.0000000000001 watts, 10 to the power of -18. The antenna at NASA's Deep Space Network, specifically the 70-meter dish at Goldstone, California, must strain to hear it. The signal is weaker than the thermal noise generated by a human body at room temperature. And yet, we hear it. Still, to understand what Voyager 1 has achieved, you need to understand where it is. Not in miles or kilometers. Those numbers have lost their meaning. You need a different scale. If you shrink our entire solar system, from the sun to the edge of the Oort cloud down to the size of a football pitch, Voyager 1 would currently be sitting just past the halfway line, moving toward the far goal. Except the far goal, the gravitational boundary of our solar system, is not 50 meters away on this scale. It is another 100,000 kilometers. The Oort cloud begins somewhere between 2,000 and 5,000 AU from the Sun. Voyager 1 is currently at 163 AU. It will reach the inner Oort cloud in approximately 300 years. It will exit the Oort cloud, fully, completely, unambiguously leaving our solar system in approximately 30,000 years. When Voyager 1 finally exits our solar system, the last human who watched its launch will have been dead for 29,940 years.
In November 2023, something happened at Voyager 1 that stopped mission scientists cold. The spacecraft began sending back gibberish, not silence, not a weak signal, gibberish, a repeating sequence of binary data that corresponded to no intelligible telemetry, no science data, no engineering readouts, just noise arriving every 22 hours with mechanical precision, as if the spacecraft were still trying to talk but had forgotten how to form words. NASA's Jet Propulsion Laboratory publicly confirmed in a statement issued on December 12, 2023, that Voyager 1 was experiencing a communication anomaly traced to one of its 3 onboard computers, specifically the Flight Data System, which is responsible for packaging engineering and science data for transmission. One of 3 computers on a spacecraft 23 billion kilometers away. The engineers at JPL could not simply reboot it. They could not upload a patch. Every command they sent took 22 hours to arrive. Every response took another 22 hours to return. Each diagnostic conversation with Voyager 1 took 44 hours. 44 hours to ask one question and receive one answer. Over the next 5 months, the team, led by Flight Systems engineer Suzanne Dodd, performed what can only be described as remote neurosurgery across interstellar space. They identified a single corrupted memory chip within the flight data system. They could not repair it, but they could, and in April 2024 they did, reroute the data packaging process around the damaged section, essentially teaching a 47-year-old computer to work with part of its brain missing. On April 20th, 2024, Voyager 1 resumed sending coherent science and engineering data. The mission had been saved, for now. But here is the thing that nobody at JPL wants to say out loud in a press briefing. The repair worked because the damaged chip happened to be in a section of memory that could be safely bypassed. The next failure may not be so cooperative. Voyager 1 runs on 3 computers, each designed in the early 1970s, before the IBM PC existed, before the internet existed, before the word software bug had entered the popular vocabulary. The total onboard memory across all 3 computers is approximately 69.63 kilobytes. 69 kilobytes. A single low-resolution photograph on your phone contains more data than Voyager 1's entire brain. And those computers are powered by 3 radioisotope thermoelectric generators, RTGs, each containing a slug of plutonium-238 that generates heat through radioactive decay, which is then converted into electricity. In 1977, those RTGs generated approximately 470 watts. Today, they generate approximately 249 watts. By 2025, NASA's own projections, published in the mission planning documents on the JPL website, indicate that total available power will fall below the threshold required to operate even one scientific instrument. One by one, the instruments will be switched off. Each shutdown is a small death. And after the instruments, the transmitter itself. We will return to that silence. But first, you need to understand exactly what will be lost when it comes. Because what Voyager 1 has been sending home these last 47 years is not just data, it is evidence that we exist.
On March 5, 1979, Voyager 1 made its closest approach to Jupiter, 349,000 kilometers above the cloud tops, and sent home images that fundamentally changed what we thought we knew about our solar system. The Great Red Spot, which astronomers had been observing since 1665, a storm older than the United States of America, was shown to be a three-dimensional vortex system of extraordinary complexity, with wind speeds of approximately 432 kilometers per hour at its outer rim. But Jupiter was not the discovery. Io was the discovery. Voyager 1 imaging scientist Linda Morabito, a 26-year-old JPL engineer, was processing navigation images on March 8, 1979, 3 days after the Jupiter flyby, when she noticed an umbrella-shaped plume erupting from the limb of Jupiter's innermost large moon. It was a volcanic eruption, active, ongoing. 9 volcanic eruptions would be confirmed in Voyager 1 imagery alone. Before Voyager 1, astronomers assumed the moons of the outer solar system were dead, cold, geologically inert rocks. Io shattered that assumption in a single photograph. But the discovery that keeps planetary scientists from sleeping well at night came from another moon, Europa. Voyager 1's images of Europa, taken at a closest approach of 733,760 kilometers, showed a surface crisscrossed by what appeared to be dark lines. No craters, no mountains. A smooth, young surface on a moon that should, by all rights, be as cratered as our own. Planetary scientist Lawrence Soderblom, reviewing the imagery in the weeks after the flyby, reportedly said the surface looked like a cracked eggshell. What was inside the egg is something we still do not fully know. The prevailing scientific consensus, supported by subsequent Galileo spacecraft observations from 1995 to 2003, and confirmed by the Hubble Space Telescope's detection of water plumes in 2013, is that Europa harbors a liquid water ocean beneath its ice shell, approximately 100 kilometers deep, an ocean containing, by volume, more than twice the total water of all of Earth's oceans combined. In the dark, under the ice, 628 million kilometers from the Sun. This is what Voyager 1 started, not with a direct discovery, but with a seed of suspicion that the solar system was not a dead place orbiting a middle-aged star, but something alive and strange and full of the preconditions for what we cautiously, carefully call life. Saturn came next, in November 1980. Voyager 1's closest approach to Saturn was 124,000 kilometers, close enough to see individual ring structures, cloud bands, and the moon Titan. Titan had been observed with telescopes since 1655, when Dutch astronomer Christian Huygens first spotted it. 325 years of human observation had told us only that it was large and had an atmosphere. Voyager 1 revealed that Titan's atmosphere was not just any atmosphere. It was thick, surface pressure of approximately 1.5 Earth atmospheres, and composed primarily of nitrogen, with complex organic molecules including acetylene, ethane, and hydrogen cyanide drifting in orange photochemical smog. Astronomer Carl Sagan, who was on the Voyager science team, described Titan's chemistry as resembling a frozen, primordial version of early Earth chemistry. He published those findings in the journal Icarus in 1981, Frozen Early Earth Chemistry, on a moon orbiting a planet 1.4 billion kilometers from the Sun. We are still processing what that means.
On February 14th, 1990, at a distance of approximately 6 billion kilometers from Earth, Voyager 1's cameras were turned back one final time to take a portrait of the solar system. The suggestion had come from Carl Sagan, who had been lobbying NASA and JPL since 1981 for what he called a family portrait of the solar system from the edge of the planetary disk. Mission director Candy Hansen and camera team member Carolyn Porco worked to make it happen. The resulting image showed Earth as a fraction of a single pixel, 0.12 pixels in size, suspended in a beam of scattered sunlight. Carl Sagan saw this image. And in 1994, in his book Pale Blue Dot, he wrote a passage about it that has since been read at funerals, quoted at the United Nations, and transmitted in radio broadcasts by amateur astronomers hoping that someone, somewhere might hear it. The thrust of it was this: everything humanity has ever done, every king and conqueror, every act of creation and destruction, every love and loss, all of it happened on that fraction of a pixel. And Voyager 1 was the first machine to show us that. After that photograph, Voyager 1's cameras were permanently shut down. Not because they stopped working, because running the cameras required power that was needed elsewhere, and because, and this is the part that strikes you when you sit with it, there was nothing left to photograph. Voyager 1 had passed beyond the realm of anything worth seeing with a camera. It was entering a region of pure physics. No moons, no planets, no sunsets, just magnetic field lines and cosmic rays and the slow diminishing push of the solar wind. And so it went dark, still transmitting, still alive, but blind. The sun does not end where the planets end. The sun's influence, its magnetic field, its stream of charged particles called the solar wind, extends far beyond Neptune, far beyond Pluto, into a vast bubble called the heliosphere. The outer boundary of this bubble, where the solar wind finally meets the interstellar medium and slows to a stop, is called the heliopause. Crossing the heliopause means leaving the sun's sphere of influence entirely, entering true interstellar space. On August 25, 2012, at exactly 18.8 billion kilometers from the sun, a distance so great that the sun itself, from Voyager 1's vantage, would appear as merely the brightest star in the sky. Indistinguishable to the naked eye from Sirius, Voyager 1 crossed the heliopause. For the first time in human history, a human-made object had entered interstellar space. NASA's plasma science team, led by Don Gurnett of the University of Iowa, confirmed the crossing not in August 2012 when it happened, but in September 2013, after analyzing plasma oscillation data. Gurnett published the confirmation in the journal Science on September 12, 2013, in a paper titled In Situ Observations of Interstellar Plasma with Voyager 1. The confirmation required a solar event, a coronal mass ejection from the sun in March 2012, whose shockwave finally reached Voyager 1 in April 2013 and caused the surrounding plasma to oscillate at a frequency that allowed Gurnett's team to measure the plasma density. The density outside the heliopause was approximately 40 times higher than inside. Not a vacuum. Never a vacuum. The interstellar medium is thin by any earthly measure, roughly 1 atom per cubic centimeter, but it is not empty. And this was the first surprise interstellar space delivered. Scientists had expected the interstellar medium to be smoother, quieter, more uniform than the heliosphere. Instead, Voyager 1's instruments found a region of unexpected complexity, fluctuating magnetic fields, plasma density variations, a particle environment unlike anything the models had predicted. Edward Stone, Voyager's chief scientist from the mission's beginning and a physicist at the California Institute of Technology, said in a 2013 press conference, "We didn't know what to expect because we'd never been there before." It is a simple statement, an obvious statement, and it is the most unsettling thing anyone has said about deep space exploration in the last 50 years. We did not know what to expect. We still don't. Every year, Voyager 1's plutonium, 238, decays a little further. Every year, the RTGs produce slightly less heat. Every year, slightly less electricity. The rate of decline is approximately 4 watts per year. That sounds manageable. Until you do the arithmetic. In 2025, Voyager 1's total available power is approximately 249 watts. Each scientific instrument requires between 2 and 10 watts to operate. The transmitter requires 23 watts. The command computer requires power to stay active. The heaters that keep the fuel lines from freezing require power. In 2025, NASA's Jet Propulsion Laboratory confirmed that Voyager 1's power budget has been reduced to the point where the team must choose, on a day-by-day basis, which instruments to keep active. In 2024, JPL shut down one of Voyager 1's 5 remaining active science instruments, a plasma wave subsystem heater, to preserve enough power for the others to continue operating. Each shutdown is irreversible. There is no switching them back on. The power budget doesn't grow, it only shrinks. The current projections, published by the JPL Voyager team on NASA's official Voyager mission page, suggest that by approximately 2025, Voyager 1 will likely need to begin shutting down science instruments permanently due to insufficient power. By approximately 2025 to 2026, the number of active science instruments may fall to 1 or 0. After that, and this is the part that the press releases tend to describe in careful, bureaucratic language, the mission team will evaluate continued operations. Evaluate continued operations means decide when to stop listening, because the spacecraft will not stop transmitting. It will keep transmitting for years after it has nothing meaningful left to say, a carrier signal, a heartbeat with no brain behind it. At some point, the Deep Space Network engineers will make a decision that no human has ever been in a position to make before. They will turn off the receiver. They will stop listening to Voyager 1. Not because it has gone silent, because listening has become pointless. The engineers, people who have spent their lives listening. There is a woman named Suzanne Dodd. She has been Voyager's project manager since 2010. Before that, she worked on Voyager in various roles stretching back decades. She is, at this point, one of the longest-serving members of the Voyager team. In April 2024, during the 5-month crisis when Voyager 1 was sending incoherent data, she gave an interview to the Associated Press in which she described the experience of waiting 44 hours for each diagnostic response. She said, "It's like talking to someone who's very far away and you're not sure they can hear you." Not sure they can hear you. The engineers who currently operate Voyager 1 were, many of them, not yet born when the spacecraft launched. They work from technical documents written in the 1970s, some of which exist only on paper, because the digital files were stored in formats that are no longer readable by any software currently available. JPL engineer Enrique Medina told Wired magazine in 2023 that part of his job involves reading technical documentation that predates his own birth. Think about what that means, structurally. A machine launched before the internet, before personal computers, before digital audio. That machine is still operating, still sending data, and the people keeping it alive are doing so using paper manuals and institutional memory, making decisions with 44-hour feedback loops for a spacecraft that is only going to get harder to communicate with every single day for as long as it continues to function. And they are doing this because the alternative, giving up, switching off the receiver, declaring the mission ended, feels to everyone involved like something that cannot be undone. There is a psychological concept called the sunk cost fallacy, the tendency to continue investing in something because of how much you've already put in, rather than because of what you'll get back. The Voyager mission is the only context in human history where the sunk cost fallacy and genuine scientific value are completely indistinguishable from each other. Because every day that spacecraft keeps talking is another day of irreplaceable data from interstellar space. There is no other way to get it. There will not be another Voyager-class interstellar probe for decades, possibly centuries. This is the only conversation we will ever have with interstellar space, and it is ending. The signal itself, what we are actually receiving. Voyager 1 currently transmits at a frequency of 8.41 gigahertz, the X-band frequency range. It sends data at approximately 160 bits per second. 160 bits per second. Your home internet connection transfers data at roughly 100 million bits per second. Voyager 1's data rate is 625,000 times slower than a modest home broadband connection. At 160 bits per second, transmitting a single high-resolution photograph would take approximately 10 days. And yet, at this data rate, using instruments designed in the 1970s, powered by a light bulb's worth of electricity, received by a dish that has to strain to hear it, Voyager 1 has been sending us continuous data about interstellar space that we cannot obtain any other way. Magnetic field strength, cosmic ray flux, plasma wave oscillations, solar wind particle counts. Every one of these measurements tells us something about the structure of interstellar space, the environment through which any future interstellar probe would have to travel, the environment through which any signal from a distant civilization would have to pass to reach us. Dr. Stamatios Krimidis, who led the low-energy charged particle instrument team on Voyager since 1972, published a paper in 2019 in Nature Astronomy describing Voyager 1's data as showing that the interstellar magnetic field is approximately 40% stronger than pre-mission models predicted. 40%. Our models of interstellar space were wrong by 40%. This is why the silence matters. Not because Voyager 1 is a symbol, though it is, but because it is the only instrument we have ever placed in interstellar space, and its death will leave a 23 billion kilometer blind spot in our understanding of the universe for longer than human civilization has existed. The golden record, a message in a bottle thrown into an infinite ocean. But let's talk about what else Voyager 1 carries, because the signal from Voyager 1 is only half the story. What Voyager 1 carries, what it will continue to carry long after its transmitter has gone dark, is something of a different order of significance entirely. The golden record. In 1977, a committee assembled by Cornell University astronomer Carl Sagan spent approximately 12 months compiling a record of human civilization to be mounted on both Voyager 1 and Voyager 2. A time capsule and a greeting card in one, intended for any extraterrestrial intelligence that might someday encounter the spacecraft. The record contains 116 images, encoded in analog form, 90 minutes of music from 27 cultures, greetings in 55 languages, and a selection of sounds: rain, wind, surf, a human heartbeat, the cries of animals, the sound of a mother's first words to a newborn child. It contains a message from then-President Jimmy Carter, recorded on July 29, 1977, which includes the words, "This is a present from a small, distant world, a token of our sounds, our science, our images, our music, our thoughts, and our feelings." There is a pulsar map on the cover, a map using the positions of 14 known pulsars relative to our sun, essentially giving any technologically advanced civilization the precise coordinates of Earth. We sent directions to our home to anyone who might find it. Carl Sagan knew this was, at best, a symbolic gesture. He estimated in 1977 that the probability of Voyager 1 encountering any star system within the next several billion years was roughly 1 in 10 billion. 1 in 10 billion. And yet the golden record is not symbolic to the people who made it. Anne Druyan, Sagan's collaborator on the project and later his wife, described the experience of composing the record in her 2019 book Cosmos, Possible Worlds. She oversaw the selection of music. She compiled the sounds, and in the process of making it, she had her own brainwaves recorded. 30 minutes of electroencephalogram data, encoded on the record, included as a meditation on what it means to be human in the 20th century. Anne Druyan's thoughts, encoded on a spacecraft in interstellar space. Right now, the golden record will not stop working when the transmitter fails. It will not decay when the power runs out. It is gold-plated copper, sealed in an aluminium case. In the vacuum of interstellar space, with no atmospheric corrosion, no temperature cycling, no UV radiation to speak of, it will last, according to astrophysicists' estimates, for at least 1 billion years. 1 billion years. The record of us will outlast us, almost certainly, and it will be traveling through interstellar space, blind, deaf, transmitting nothing, carrying everything, for longer than the Earth has existed, waiting for someone to find it who has hands to hold it and a mind to understand what it means. The moment that makes you feel genuinely small, we need to stop here and confront something. Because everything we've discussed so far, the 23 billion kilometers, the 22-hour signal delay, the interstellar medium, all of it takes place in a region so close to Earth, on cosmic scales, that it barely registers. The nearest star to our sun is Proxima Centauri. It is 4.24 light-years away. 1 light-year is approximately 9.46 trillion kilometers. Proxima Centauri is 40 trillion kilometers from Earth. Voyager 1, after 47 years of continuous travel at 61,197 kilometers per hour, has covered approximately 23.5 billion kilometers. That is 0.06% of the distance to the nearest star. Not 6%, 0.06%. If the distance from Earth to Proxima Centauri were the length of a football pitch, 100 meters, Voyager 1 would currently be 6 centimeters from the starting line. 6 centimeters. After 47 years. At its current speed, Voyager 1 would reach Proxima Centauri in approximately 73,775 years. The entire recorded history of human civilization spans roughly 5,000 years. We launched a machine toward the stars, and it will arrive at the nearest star in a time frame that is 15 times longer than all of recorded human history. And Proxima Centauri is the closest star. The Milky Way galaxy contains an estimated 100 to 400 billion stars. The nearest large galaxy, the Andromeda Galaxy, is 2.537 million light-years away. The observable universe contains an estimated 2 trillion galaxies. 2 trillion galaxies, each containing hundreds of billions of stars, each star potentially surrounded by planets. And our boldest act of exploration, the most distant journey ever undertaken by our species, has covered 0.06% of the distance to the nearest star. We are not at the beginning of understanding our universe. We are at the beginning of the beginning. And the machine that represents that beginning is dying. After the silence, what happens next? So, the silence. What actually happens when the last signal from Voyager 1 is received? Not the metaphor, not the poetry. What actually, mechanically, physically happens? At some point, the JPL team's current best estimate suggests sometime between 2025 and 2030 for the final instrument shutdown, with the last carrier signal possibly continuing until approximately 2036. The electrical power from the RTGs will fall below the threshold required to maintain the transmitter. The transmitter will shut down. It will not be a moment anyone witnesses directly, because the last signal will have left Voyager 1 22 hours before anyone on Earth knows it is the last signal. The Deep Space Network operators at Goldstone, or at the Canberra facility in Australia, or at the Madrid station in Spain, whoever is on duty during the relevant 22-hour window will be listening to the carrier signal from Voyager 1 on their instruments. A faint but persistent line on the display. And then, at some point, without announcement, without ceremony, without any indication that this moment is different from any of the thousands of moments before it, the line will disappear. The operators will not immediately know if this is a fault in their equipment, a temporary dropout, a spacecraft anomaly that might be recoverable, or the end. They will run diagnostics, they will switch receiving dishes, they will wait. And after sufficient time has passed, after the window during which a recoverable fault could plausibly explain the silence is closed, someone will write an entry in the mission log, a line of text, a timestamp, a status code, and Voyager 1 will cease to be a mission and become a monument. Still out there, still moving, still carrying the golden record, still radiating heat from its decaying plutonium, but silent. And here is the thing about that silence. The thing that the press releases will not say, that the official mission closure documents will carefully avoid, the thing that will settle into the minds of the JPL team in the days and weeks after, and never quite leave. We will have no idea what happens to Voyager 1 after that. Not for 73,000 years. Not until, if we still exist, if we have developed propulsion capable of interstellar travel, if any of the 10,000 things required for that to happen have come to pass, something or someone encounters it. After the silence, Voyager 1 enters a condition that has no precedent in human experience. It becomes the longest-running message we have ever sent that we will never know was received.
In 1972, a 28-year-old aerospace engineer named Gary Flandreau, working at JPL, realized that a rare alignment of the outer planets, an alignment that occurs only once every 175 years, would allow a spacecraft to visit all 4 of the outer gas giants in a single continuous trajectory, using each planet's gravity to accelerate toward the next. This alignment would be in position starting in 1977. If NASA didn't launch in 1977, the next opportunity would be 2152. The decision to launch, to commit the engineering resources, the funding, the institutional will, was made with extraordinary speed. The mission was authorized in 1972. The spacecraft were designed, built, and tested in 5 years. Voyager 1 launched on September 5, 1977. The window was hit. The mission flew. But here is what nobody celebrates about this story. The people who made that decision, who built that spacecraft, who aimed it with the precision required to thread the gravitational needle of 4 giant planets and arrive at interstellar space 47 years later, those people could not have known when they built it that it would still be running in 2025. They built it for 5 years. It has been running for 47. They designed it with margins they didn't believe would ever be needed, with redundancies they thought were over-engineering, with transmitter power that seemed excessive for a 5-year mission. And those margins, those redundancies, that excessive power, they are the only reason we are still in contact today. There is a lesson in this that goes beyond space exploration. When we build things, spacecraft, institutions, ideas, with the conviction that they will be temporary, that they will be replaced, that their relevance will expire on a schedule we can predict, we build them smaller than we should. We build them to last 5 years. When we build things as if they might matter to people we will never meet, as if the margins and redundancies might be used by engineers who haven't been born yet, to receive data from a universe we don't yet understand, we build them like Voyager. NASA's Jet Propulsion Laboratory has been training new engineers on the Voyager mission since the 1990s, specifically because the original team is aging, retiring, and dying. The institutional knowledge required to maintain contact with Voyager 1 is, in itself, a kind of record that must be preserved and transmitted. Former JPL director Charles Elachi, in a 2017 interview with the New York Times, described the Voyager mission as the longest continuously running experiment in the history of human science. And the act of continuing it, of choosing, year after year, to keep the receiver pointed at that tiny signal in Ophiuchus, is its own statement about what we value as a species. After Voyager 1's signal ends, the Deep Space Network dishes will, of course, not go dark. They are already listening to dozens of other spacecraft. The Parker Solar Probe, the James Webb Space Telescope's communications, the Mars orbiters and landers, the Juno spacecraft at Jupiter. The dishes will pivot. They will lock onto other frequencies. They will continue their work, but there will be a frequency they no longer monitor, a coordinate in Ophiuchus that they no longer track. And in that absence, in the cessation of listening to that particular point in the sky, something will have ended that began before most currently living humans were born. The question that should linger here, the question that the scientists at JPL live with, that the engineers who have dedicated careers to this mission carry home at night, is not what did Voyager 1 find. That question has been answered, richly and in extraordinary detail. The question is, what did we fail to build next? Voyager 1 launched in 1977. Since then, no mission has been designed with interstellar space as its primary destination. No follow-up probe has been approved, funded, and launched. There have been proposals, notably the Interstellar Probe study led by Ralph McNutt of Johns Hopkins University Applied Physics Laboratory, which was formally studied by NASA in 2021 and estimated to cost between $1.6 billion and $2 billion USD, but no approval, no funding, no launch date. The current roadmap, as of 2025, contains no approved interstellar mission. We will lose our only data source for interstellar space, and we have made no concrete plans to replace it. After the signal ends, Voyager 1 will continue on its current trajectory, roughly in the direction of the constellation Ophiuchus, angled 35 degrees north of the ecliptic plane. In approximately 40,000 years, it will pass within 1.6 light-years of the star Gliese 445, a red dwarf in the constellation Camelopardalis. Not close enough to be captured by that star's gravity, but close enough that if any civilization orbiting it has instruments of sufficient sensitivity, the thermal signature of Voyager 1's decaying RTGs might be detectable. A whisper of heat, after 40,000 years of silence. After that close approach, Voyager 1 will continue into the deep reaches of the Milky Way. It will not reach the galactic center for approximately 225 million years. It will not leave the galaxy in any timescale that has meaning in human terms. The spacecraft will be here, in this galaxy, moving, carrying its record, radiating the last wisps of plutonium heat, long after the sun has expanded into a red giant and consumed the Earth. Long after every other artifact of human civilization has been destroyed, long after us. And this is the thought that changes the texture of the universe once you sit with it. We are not permanent. Our cities are not permanent. Our civilizations, our languages, our accumulated knowledge, our art, our science, none of it is permanent. But Voyager 1 is as close to permanent as anything we have ever made. And the only part of Voyager 1 that was designed with permanence in mind, the Golden Record, contains no scientific data, contains no engineering schematics, contains no map of Earth's industrial infrastructure or academic libraries or military installations. It contains music. It contains the sound of rain. It contains Anne Druyan's thoughts. It contains, in the words Carl Sagan wrote on the cover of the Record's official companion book, published in 1978, the sounds of a planet. That is the message we chose to send. Not our achievements, not our power. The sounds of a planet. Here is the question that should keep you awake. Voyager 1 is 47 years old. It has covered 23.5 billion kilometers. It has crossed the heliopause. It is transmitting from interstellar space, and it is, by any measure, a primitive machine. Its computers have 69 kilobytes of memory. Its camera, when it still worked, had a resolution of roughly 800 by 800 pixels. Its power source is a technology that has barely changed since the 1950s. If we, a civilization that has been doing science for approximately 500 years and spaceflight for approximately 70, can send an object to interstellar space, however slowly and however primitively, then what can a civilization do that has been doing this for 5,000 years? For 50,000 years? What can a civilization do that is as far ahead of us as we are ahead of the engineers who first observed Jupiter through a telescope in 1610? And if such civilizations exist, and the mathematics of a universe containing 2 trillion galaxies makes their non-existence the extraordinary claim requiring extraordinary evidence, then some of them may have sent their own Voyagers, millions of years ago. Some of those Voyagers may carry records of their own. Some of those records may have passed through our solar system already, silent and dark, while we were still figuring out fire. Some may be passing through right now, and we would have no way to know, because the universe does not announce itself. It waits. There is a version of this story that is only about loss. The loss of a signal, the end of a mission, the silence that follows the last transmission of the most distant machine in human history. That version is true. But there is another version. The other version is this. We built something in 1977 that is still operating in 2025. We launched a machine into a void we didn't understand, and it sent back data that rewrote our picture of the solar system, and then of interstellar space, and then of our own smallness. We built something that will outlast everything else we have ever made. We pressed the sounds of rain and music and a mother's first words into gold, and we threw it into the universe like a prayer. And somewhere, 23.5 billion kilometers from here, in the dark between the stars, a machine the size of a small car is still making its way through the night. Still alive. Still talking. Still ours. For now. The next question, the one that follows naturally from everything we've just discussed, is this. The universe is 13.8 billion years old. Life on Earth took 3.5 billion years to produce a mind capable of asking why it exists. We have approximately 5 billion years before the sun makes the question irrelevant. What are we going to do with the time we have left? That's the next video. Don't go far.